Hi, and welcome to the video on solving exponential and log equations. We're going to be doing all kinds of equation solving today, so let's get started. All right, let's remember that exponential equations are equations that have the variable in the exponent, just like exponential functions or functions that have the variable in the exponent. Here are some examples of some exponential equations that we're going to learn how to solve. Let's go ahead and start with the very first type. And the first type of equations exponential equations we're going to solve are going to be exponential equations that have like bases. So let's go ahead and jump in. So the first equation says 5 to the t equals 125. Well, at this point, you're probably starting to recognize some powers of numbers. So we know that 125 is equal to 5 cubed. So this equation says 5 to the t equals 5 to the third, and therefore t must be equal to 3. Similarly, for the second one, 2 to the w equals 2 to the what? Well, we know 64 is the power of 2. Let's count it up. 2 times 2 is 4, 8, 16, 32, 64. 64 can be written as 2 to the fifth. So this tells me that w equals 5. And this last one is a little bit more complicated. We have 3 to the 2x plus 1, and we know 27 is a power of 3. It's 3 cubed. So this tells me that 2x plus 1 must be equal to 3 because this tells me that 2x plus 1 must be equal to 3 because those two exponents are the same, and we solve this for x. So subtract 1 from each side. That gives me 2x equals 2. Divide by 2, and I get x equals 1. So there's my solutions. It's always a good idea to check your solutions. The first two were so straightforward we couldn't even check them. But this would be 3 to the 2 times 1 plus 1 equals 3 cubed, which in fact does equal 27. So check. So that's a special situation that comes up if you happen to have the same base exponents with the same bases on both sides of the equation. But what happens if you don't? Like 5 to the v minus 3 equals 137. 137 is not a power of 5, so we can't use this method to solve that type of equation. So the way we use to solve those equations is we rely on the power property of logs, which we learned in an earlier video. And the power property says log of m to the p equals p times log of m. So we're going to use this to solve the exponential equations with logs. So what we're going to do here is we have 5 to the v minus 3 equals 137. And the first thing we're going to do is we're going to take a log of both sides. And I'm just using log base 10. Log of 5 to the v minus 3 equals log of 137. And I should use parentheses. I get kind of lazy about it sometimes. Now using our power property, the v minus 3 comes down out of the exponent in front of the log. And that's the key to using logs to solve exponents, is it gets that variable out of the exponent. And this becomes v minus 3 times the log of 5 equals the log of 137. And now we need to solve this equation for v. There's a couple different steps you could do in solving this. I'm going to first just divide both sides by log 5. These cancel because we're undoing multiplication with division. I get v minus 3 equals log 137 minus log 5. And now I need to add 3 to each side. And this gives me v equals log 137 over log 5 plus 3. Now, that is actually a fine answer. It doesn't look great if you're not used to looking at it, because log 137 is kind of a weird-looking number. It's not what we're used to seeing. But this is a fine, exact solution. If we're doing a story problem, or if they ask us to approximate, we can use our calculator to approximate this. Let's go ahead and pull our calculator up. And we can do log of 137 and that would be equal to about 2.14 over log of 5, which is 0.7 plus 3. So let's go ahead and calculate that. So 2.14 divided by 0.7 plus 3, about 6.06. Right? So there's an approximate solution. All right, let's try another example. Here we have e to the 4x minus 7 equals 11,243. Oh, I should totally check this solution. All right, so that's our approximate solution. Let's go ahead and check our answers just to practice. It's nice solving equations because you get to check your answers. I'm going to check with the approximate solution to just see if I get close. So I'm going to check that 5 to the 6.06, and for my variable v, minus 3 is about equal to 137. So let's go ahead and grab our calculators and check that. So we're going to do our 6.05, which we already have in there. We're going to subtract 3 from that. We're going to take 5 to the power of 3.06-ish. 5 to the 3.06. And we get 137.67. Now, since we're approximating, we're not going to get exact values. And I've been rounding pretty ruthlessly here. So this is definitely the correct approximation. All right, let's try another example. Let's solve exponential equations. Another example of solving exponential equations with logs. This equation says e to the 4x minus 7 equals 11,243. So to get that 4x minus 7 out of the exponent, I want to use logs. You don't have to use natural logs, but it makes it easier if the base is e if you use natural logs. So I'm going to take the natural log of both sides, or log base e. And I get natural log of e to the 4x minus 7 equals the natural log of 11,243. My 4x minus 7 comes down out front. And we remember that the natural log of e is equal to 1 because e to the 1 is e. So this is just 1. So this left-hand side becomes 4x minus 7 times 1, which is just 4x minus 7. And now I have 4x minus 7 equals the natural log of 11,243. I'm going to add 7 to each side. 4x equals the natural log of 11,243 plus 7. And divide the whole thing by 4. So x equals the natural log of 11,243 plus 7 all over 4. And again, that is my exact solution. Let's go ahead and get an approximate solution and check our answer. So let's approximate this with a decimal. So we're going to take 243, and take the natural log of it. We'll add 7 to that. And we'll divide that by 4. And I get about 4.08. So that's my approximate solution. This is my exact solution. And let's go ahead and check our answer. So I'm going to plug 4.08 in for x. E to the 4 times 4.08 minus 7, and hope I get something close to 11,243. So it's 11,158, close, not great, but that's due to all the rounding. All right. Oops, wrong button. I want you guys to give this one a try. It's a little bit trickier, but go ahead and give it a try. Pause the video and see what you do. All right, how did it go? Let's go ahead and just take logs of both sides. So log of 7 to the 2w plus 1 equals log of 3 to the w plus 2. So this becomes 2w plus 1 log 7 equals w plus 2 log 3. All right, let's distribute this all out and group our terms together. So we have 2 log of 7 times w plus log of 7 equals, so I just distributed that log of 7, log of 3 times w plus 2 log 3. Let's get all of our w terms on one side and our non-w terms on the other. So I'll subtract log 3w from both sides. And I will subtract log 7 from both sides. So that gives me 2 log 7 times w minus log 3 times w equals 2 log 3 minus log 7. Now on the left-hand side, I'm just going to factor out the w to get 2 log 7 minus log 3 equals 2 log 3 minus log 7. And then I am running out of space. I did not give myself enough space in this problem. Oh, that's crazy. Let's squeeze it in over here. We're going to just squeeze it in. And I'm going to divide both sides by this 2 log 7 log 3. Okay? So over here, let me just draw a little squeezy line. I wish I'd give myself more room. I would have w equals, my right-hand side here is in the numerator, 2 log 3 minus log 7 all over, and then what I divided by, 2 log 7 minus log 3. And that is my final exact answer. Now, it would be a good exercise to get a decimal approximation for that and check. I'm not going to do it right now because I don't want this video to get too long. We have quite a few more equations to solve, but that would be a good exercise for you to do right now. All right, sometimes when you're solving exponential equations, you have to do a little bit of work before you take the logarithm. So what I wrote over here, it says, if necessary, let's isolate the exponent first. So what we're going to do here is we're going to have to do a little bit of algebra first before we get started. Well, the first thing I'm going to do is I'm going to divide both sides by 4. Divide both sides by 4. And I just did that because 4 goes into 12 and 12 doesn't go into 4. So that gives me 3 times 1.07 to the t equals 1.06 to the t. And now I'm going to divide both sides by 1.07 to the t. And that gives me 3 equals, and since these have the same exponent of just t, I can make it 1.06 over 1.07 to the t. All right, and now I'm down into my situation where I can just take the logs of both sides. So log 3 equals log 1.06 over 1.07 to the t. The t can come down in front, and I get log 3 equals t log 1.06 over 1.07, and then I just divide both sides by log 1.06 over 1.07. So my final answer is t equals log of 3 divided by log 1.06 over 1.07. Kind of have a short parenthesis there. So again, this is my exact solution. If I wanted to find a decimal solution, I could just plug all that in the calculator and get a decimal, and then I would check my work with that. All right, why don't you guys try this one? So isolate the exponent first and then solve using logarithms. How'd it go? Let's find out. Well, the first thing I'm going to do is divide by -2. 3 to the 5x equals -9. Take the log of both sides. Log of 3 to the 5x equals log of -9. Bring down the 5x. Log 3 equals log -9. And divide by 5 log 3. So x equals log -9 over 5 log 3. Well, we plugged along with all this algebra, but does anybody see anything wrong with this? Because I do. Right here, we cannot take log base 10 of -9. You can't take the log of a negative number. And if we go back up to our original problem, if we think about taking 3 to the 5x, that's always going to be positive. If we multiply that by -2, it's always going to be negative. There's no way we can make this be equal to 18. So this is an example of where you really do have to check all those solutions, because sometimes you can just be doing the algebra and the logs get away from us. So if we were to check this one with our calculator, like I've been talking about doing, and we tried to put this in here, we would go -9 and try to take the log, and it would be invalid input, and be like, oh yeah, you cannot take the log of a negative number. So this actually has no solution. All right, let's solve some logarithmic equations. Logarithmic equations are equations that have the variable in the logarithmic expression. Usually when we solve these, we'll be solving something like log of 3 times x equals 10, or this big natural log equation that we're going to try and find the value for z that makes that true. You're going to be having to use a lot of information you know about logs, properties of logs, to solve these. The first method we're going to use is just switching it to exponential form and then, of course, checking our answers. So here we have log of z minus 7 equals 2. We know this is log base 10 because there's nothing written. So rewriting this in exponential form would be 10, that's our base. 10 to the 2 equals z minus 7. So that means 100 equals z minus 7. Add 7 to each side, and that tells me z equals 107. And I always check it because things can go crazy with logs. Log of 107 minus 7 is equal to 2, question mark. Well, that would be log of 100, and sure enough, 10 squared is 2, so that is true. Let's try another one. Now this one's just a little bit more complicated. We're going to do the same basic pattern, except for we have a new step 1, which is to isolate the log completely and then switch to exponential form and check your answer. So on this one, the first thing I'm going to do is divide that by 6 to get rid of that coefficient. And that tells me the natural log of 2x equals 5. Switching this to exponential form, remember my base here is e. E to the 5 equals 2x. Divide both sides by 2. And I get x equals e to the 5th over 2. Now that is my exact solution. E is just a number like pi or any other number. We can leave it like that. If we want to find a decimal approximation to check it, which is a good idea, we can pull up our calculators and compute e to the 5th over 2. So we're going to go second. 5 e to the x divided by 2, and we get about 74.2. So let's check that in our equation. Our equation said 6 times the natural log of 2x. So I'm going to take 74.2, times it by 2, take the natural log of that value, and multiply that by 6, and I got 29.999, which is very close to 30. I'm saying that that is a correct answer. Just a little bit off from my rounding. All right. Here's example 9. In this example, it may be more convenient to reduce our equation to have a single logarithm, then switch to exponential form and check our answer. There's more than one way to solve these problems, but this is the way I'm going to try it. The first thing I'm going to do is I'm going to add that log 4 to the other side of the equation. And now I'm going to use my multiplication property of logs to write log of y minus 1 times 4 equals 5. So now I'm going to rewrite using exponential form. My base is 10. So 10 to the 5th equals y minus 1 times 4. All right, so 10 to the 5 is 1 with 5 zeros, which is 100,000. And that's equal to y minus 1 over 4. Divide both sides by 4. And we get 25,000 equals y minus 1. So y equals 25,001. With logs, it's always a good idea to check our solution. So let's go ahead and check this. We're going to figure out if log of 25,001 minus 1 is approximately, since we're using decimal approximations to check, 5 minus log of 4. All right, so let's go ahead and use our calculator. Oh, whoops, I didn't mean to do that. Okay, so clear this out. All right, so let's use our calculator to check this. We're going to take the log of 25,001 minus 1. So I'm just going to put in 25,000. I'm going to take the log, and I get about 4.4. And now I'm going to do log 4. Oops, I don't think I hit log of it. Okay, and then I'm going to subtract that from 5. So 5 minus 0.6. And sure enough, that is 4.4. So we feel pretty good about that answer. All right, let's keep going. A couple more problems to go over here. All right, so I would like you guys to try this example 10. So use your properties of logs to make this into a single logarithm. Switch it to exponential form and then check your answer. All right, how'd it go? Let's give it a try. Well, this one was a little bit tricky. I have 2 logs being subtracted, so that's the quotient property. So it's log of t plus 2 over t minus 1 equals 1. Rewriting that in exponential form, I have 10 as my base, so 10 to the 1 equals t plus 2 over t minus 1. I need to solve this equation. There's a couple different ways you can go about solving this. A lot of people like to just think about this as 2 fractions or 2 proportions. So 10 to 1 is the same as t plus 2 over t minus 1, and then you just cross multiply. So 10 times t minus 1 equals 1 times t plus 2. So 10t minus 10 equals t plus 2 minus t from both sides, add 10 to both sides, 9t equals 12. Divide by 9, and we get t is equal to 12/9 or 4/3. So this isn't a case where you wouldn't really want to write this as 1.3. That's not an exact solution. Our exact solution is 4/3. Let's go ahead and check this. Is the log of 4/3 plus 2 minus the log of 4/3 minus 1 equal to 1? Let's use our calculators to help us out with this checking. And we're going to do 4/3 plus 2. So I am just going to use 1.3 for my checking procedures. 4 divided by 3 plus 2. Take my log. And that gave me about 0.52. And then 4/3. 4 divided by 3 minus 1. Take my log, and I get negative 0.48. And now I'm careful with my signs, and I have 0.52 minus negative 0.48. Sure enough, that is going to be 1 because those guys add together. So I feel pretty good about that. All right, one more problem to do, the hardest one yet. We'll do this one together. All right, and this one's called extraneous solutions for a reason. So we have a log equation. We see that we have 2 logs being added. We're going to use our product property to give us log t plus 2 t minus 1 equals 1. We're going to switch it to exponential form. 10 to the 1 equals t plus 2 times t minus 1. This is a quadratic equation. I recognize that. I know when I want to solve quadratic equations, either using factoring or the quadratic formula, I have to set it equal to 0, which means I have to multiply this all out and set it equal to 0. So let's FOIL this out. T squared minus t plus 2t minus 2. 10 equals t squared plus t minus 2. Set it equal to 0. 0 equals t squared plus t minus 12. So I can try factoring or I can try quadratic formula. I'm going to use factoring because I think I can factor this pretty straightforward. I need two numbers that multiply to negative 12 and add to positive 1. I'm going to go with positive 4 and negative 3. So double check t squared minus 3t plus 4t. Yep, sure enough. So using the zero product property, I know t is equal to either negative 4 or t is positive 3. So now I need to check my solutions. Those are my two solutions to this equation. I'm going to check them one at a time. Let's check t equals negative 4. So that gives me log of negative 4 plus 2 plus log of negative 4 minus 1. Is that equal to 1? So that's log negative 2. And right off, I'm like, ooh, no. You cannot take the log of a negative number. This one's also going to be negative. That is not going to be a solution because you cannot take the log of a negative number. I think this positive 3 is going to work out a lot better. 3 plus 2 plus log of 3 minus 1. Is this equal to 1? So this is log 5 plus log 2 equals 1. We don't even need a calculator for this because we know the multiplication property of logs. That's going to be log of 5 times 2, which is 10, and 10 to the 1 is 10. So we feel good about that. All right, that's the video on solving exponential and log equations.